Welcome viewers, in this video we will see the DC transient response of RL circuit, case 1 rise of current. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. Link is given in the description box. Now we will go to the topic DC transient response of RL. Resistance and inductance are connected in series circuit. The case 1 rise of current. Let RL series combination be impressed upon the DC voltage E by closing the switch K. Resistor and inductor is connected in series, that is energized by the voltage E, DC voltage source E, that is by closing the switch K. Assume that current through the inductor before closing the switch is 0. So before closing the switch there is no current, there is no flow of current. Let K be the closed at the instant t equal to 0. Switch is closed at t equal to 0. Now consider this diagram, circuit diagram. So this is the RL series circuit. R and L is connected in series, energized by the DC source and controlled by the switch K. The voltage across resistor is ER, voltage across inductor is EL. Right. So after closing the switch, this closed at t equal to 0, the circuit behave like this. The inductor acts as a open circuit. This is a voltage source, resistor, and it will act as a open circuit. Right. Now we'll go for, in order to find the time response, we need to apply the KVL, Kirchhoff's voltage law, to this circuit, and we need to find the equation. Then we can apply Laplace transform and inverse Laplace transform to get the time response. Okay, while applying the Kirchhoff's voltage law, what will happen? The applied voltage E equal to voltage drop across resistor and inductor. So E equal to R into I plus L di by dt. R into I is the voltage drop across resistor, L di by dt is the voltage drop across inductor. Right. So according to KVL, the voltage, this is voltage rise, this is voltage drop, both are equal. So voltage applied E equal to drop across R and L. Right. Now we'll see the diagram how to apply the Kirchhoff's voltage law. So the equivalent circuit at T0 plus is shown in figure B, that is inductor is open circuited. T0 plus means after closing the switch. The inductor is shown as a open circuit. Hence I0 minus equal to I0 plus equal to 0, because before closing we assume that there is no current flow. After closing it is act as a open circuit. So current before closing the switch, after closing the switch is 0. Right. Then we'll go for the applying the Kirchhoff's voltage law to the circuit after t seconds of closing K. After closing the switch we can apply the Kirchhoff's voltage law. We already discussed the applied voltage E equal to resistive drop plus inductive drop, Ri plus L di by dt. You take, this is the equation number 1. Resistive drop, inductive drop, that is equal to E, applied voltage E. Now we can take the Laplace transform on both the side by converting t domain into s domain. Again by taking inverse Laplace we will get the t domain, time response. First we will take the Laplace transform. So while taking Laplace transform, it is nothing but R into I of t become I of s plus L. This di by dt is nothing but s into I of s minus I0 plus. This is the initial condition. That is equal to Laplace transform of E is E by S. Right. So R into I of s plus L of s I of s minus I of 0 plus, that is equal to E by S. Right. So di by dt, Laplace transform of di by dt is s into I of s minus initial condition. Then R into I of s plus L, s into I of s, this initial current. We already discussed that the current before closing, after closing the switch is 0. This value is 0. That is equal to E of s. Now we will take the I of s outside. So that R plus s into L, that is equal to E by s. I of s equal to R plus SL equal to E of s. Now we can go for the further simplification. So that I of s equal to E divided by s into R plus L of s. This term is brought in the denominator. Now we'll take the L outside. So that Already S is there, L into S plus R by L. While taking the L outside, this becomes S. Here L is not available, so that R by L. So now in order to bring S plus form, S plus R by L, we are taking L outside. Now take this equation number 2. So I of S equal to E divided by L into S of S plus R by L. Right. Now we'll take the partial fraction. In order to take the inverse Laplace, we need to split the term. Then only we can take the inverse Laplace. Let us consider E divided by Ls into S of R divided by L can be written as A by S plus B by S plus R plus A, R by L. This is called a partial fraction. So the S, the terms, two S terms are splitted. Then only we can able to find the inverse Laplace transform. Now we can go for the simplification. So this term E divided by Ls of S plus R by L equal to, take the LCM, S into S plus R by L. Here S is available, so it is multiplied with this term. Here S plus RL is available, so multiplied the S, right? So A into S plus RL plus B into S. These terms are multiplied. This term is multiplied with A, this term is multiplied with B in order to simplify. Now this S got cancelled. Similarly, S plus RL also available on both the side, right? So after cancelling the term, we will see that what happened. E by L equal to A into S of R plus L plus BS, right? This denominator terms are cancelled. This is equation number 4. E by L equal to A of S plus RL plus BS. Now what the next step is, we need to find the value of A and B. Then only we can go for inverse Laplace transform. Then how to find that? By putting S equal to 0, we can, this term got cancelled, so that we can find the term A. By putting S equal to minus R by L, this term become 0, so that we can find the term B. So that is our idea, right? Put S equal to 0, so that we can find value A. Put S equal to minus R by L, so that we can find the value BS, right? First we will put S equal to 0 in equation number 4. This is the equation number 4. So while putting S equal to 0, what happened? E by L equal to A into this S is 0 plus R by L plus B into S is 0. So this term becomes 0. So E by L equal to A into R by L. L got cancelled. So E equal to AR. So A equal to E by R, that is A equal to E by R. Right. So that now we calculate the term A, constant. A is E divided by R. Right. Now we need to find the term B. In order to find the B, we are substituting S equal to minus R by L. This S is substituted as minus R by L in equation number 4. Now substitute S equal to minus R by L in equation 4, so that E by L equal to A plus, this is S. S is replaced by minus R by L plus R by L plus B into minus R by L. So this is minus R by L plus R by L, so got cancelled. It become 0. So E by L equal to A of 0, here negative available, minus B into R by L. So that E by L equal to minus B into R by L. L got cancelled. E equal to minus BR, so that minus B equal to E by R. That is B equal to minus E by R. Right? Now we calculated the constant B also. A already calculated as E by R, B equal to minus E by R. Now we can substitute this value and we can go for the inverse Laplace transform. Substitute the value of A and B in equation number 3. So this is equation number 3. E divided by Ls, S plus R by L equal to A by S plus B by S plus R by L. Right? So A is substituted as E by R, B is substituted as minus E by R. So that it is nothing but E divided by S into R minus E divided by R of S plus R by L. Right? So now we can take this E by S, E by R is commonly available. So E by R is taken outside. So that E by R of 1 by S minus 1 divided by S plus R by L. So take this equation number 5. Right. Now we'll go for the further. So this this term now is replaced as this E by R of 1 by S minus 1 by S plus R by L, right. Substituting the above value in equation number 2, second equation, so that I of S equal to E divided by Ls S plus R by L. This is equation number 2. So now this value is replaced by E by R of 1 by S minus 1 by S plus R by L, right. So this time we cannot take the inverse Laplace, so that we use the partial fraction. We identify the value of, we calculated the value of A and B, that is substituted. After substitution we got this. Now we can easily take the Laplace transform on both the side, inverse Laplace on both the side. So while taking inverse Laplace, this I of S become I of t, then E by R. 1 by S, the inverse Laplace of 1 by S is 1. Similarly 1 divided by S plus R by L is nothing but this, using this formula. 1 divided by S plus A equal to E power minus AT. This is the Laplace transform. So 1 divided by S plus R by L. Here A is nothing but R by L. So that E equal to minus R by L t. Right. So inverse Laplace of this 1 divided by S plus RL is E of minus RL by t, based on this formula, E of minus AT. Now this is equation number T. So this is the time response of the RL circuit, case 1, rise of current. We got that I of t equal to E divided by R of 1 minus E power minus RL by t, R by L into t. Right. Now we'll go for the further analysis. I equal to E by R is called a steady current. E by R. This E by R can be written as I. Then L by R is the time constant of RL circuit. L by R equal to tau, that is time constant. So based on that we can write I equal to capital I, steady current of 1 minus t into tau. This t is written as it is R by L, minus R by L, but L by R is tau, but here R by L, so 1 by tau. So minus t by tau. See equation number 8. So I equal to I, steady current of 1 minus E power minus t by tau. By analyzing the nature of this equation, the above equation shows that as t increases, I increases exponentially. So when the current increases, when the time increases, current also increases exponentially. Actually this term is decreasing, but 1 minus is there, so that it is increasing, right. So t increases, I also increases. Now we'll go for further analysis. The transient voltages ER and EL across R and L respectively during the rise of current in the inductor can be expressed as. Now we calculated the time response of the current. Now we'll calculate ER and EL, voltage across resistor and inductor. So ER is nothing but R into I, resistor value into I. So R into I is already calculated, I of 1 minus E power minus t by tau, right. Similarly ER equal to E into, so this R, I into R is written as E, right, applied voltage, 1 minus E power minus t by tau. So this equation number 9. So this equation number 9, we can say that voltage across R increases exponentially from 0 to E during the rise of current. Already told this is the decreasing, but 1 minus t means increasing, right. So when the rise of current, the voltage is increases from 0 to E, is a rise, increasing, voltage increasing from 0 to E during the rise of current. Similarly what is the voltage about, voltage across the inductor, EL. So by using the Kirchhoff's voltage law, ER plus EL equal to E, we already discussed. So EL equal to E minus ER. The ER is already calculated, E into 1 minus E power minus t by tau, voltage across the resistor. Thus E is commonly available, so we can cancel. We can this is multiplied inside, E minus multiplied, minus E plus E into minus t by tau. This E got cancelled. So only we have E. EL equal to E power minus t by tau. From equation 10, we can say that the voltage across L decreases with the time t exponentially. Already told, this is the decreasing part. In previously what we have 1 minus e power. So that decreasing, but because of 1 minus it is increasing. But here 1 minus not available. Only this term is available. So that decreasing. Voltage across the inductor decreases when the time increases. Right. So this variation of I of t is shown in the diagram. Similarly, ER and EL also shown in the next diagram. Diagram A shows the variation of the current I of t. Diagram B shows the variation of ER and EL. Right. So we already discussed that it is a increasing. The current is increases with respect to time. When the time increases, current is increasing. So this is about 0.632 times of I at the time t. Thereafter it is increases. This is the total current. I equal to E by R, steady current. Right. So after analyzing, we are able to say that when the time increases, the current through the circuit increases exponentially. Right. Similarly, voltage across the resistor also increasing from 0 to E. But the voltage across inductor is decreasing. We already discussed that it is keep on decreasing exponentially. Right. So current increases exponentially with respect to time. Voltage across the resistor also increasing exponentially with respect to time. The voltage across the inductor decreasing exponentially with the time. Now we'll go for the time constant of RL circuit. Now definition of time constant T for RL circuit. Substitute tau equal to T in equation 8. So I equal to I of 1 minus e power minus t by tau. Now we are replacing tau equal to t. So minus t by t is nothing but minus 1. I equal to I of 1 minus e power minus 1. So that is I equal to I 1 minus, this is nothing but 1 by e. Either e power minus 1 or 1 by e. That value is 0.3679. So 1 minus this value is 0.6321. So I equal to 63.22 percentage of I. So this only we saw in the graph. The current increases gradually. After 63.2, it is up to this value, it is increasing exponentially, rapidly. Thereafter, slowly increasing. So this is the 63.22 percentage of current. Corresponding time also indicated in the graph. Right. So from this we can able to conclude that thus the time constant of RL series circuit is defined as the period during which the current rises to 63.2 percentage of its final value or steady value. Right. So this is the time constant. While the time taken to reach 63.2 percentage of current is nothing but a time constant of the RL series circuit. So in this video we discuss about the DC transient response of RL circuit. R and L is connected in series. For the case 1, rise of current, we discuss how the current behaves as well as voltage across the inductor and voltage across the resistor. Finally we calculate the time constant. 63.2 percentage of current reaches, that is called a time constant of RL circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.